Hello, everyone. In today's lecture, I will be introducing to you the formal study of probability. This will involve introducing some basic rules for how to calculate the probability of various sentences. Then, in the next couple lectures, we'll be introducing more and more complex or sophisticated rules. And throughout all of these lectures, we will also be looking at how to apply these rules to calculate probabilities. So let's get started. So today we'll be looking at some of the basic rules or concepts of how to calculate probabilities in a formal way. So this lecture will be split up into two videos. In the first video, this one, I will introduce an example with a coin and some questions that arise about the probability of various outcomes of flipping that coin. Then I will introduce some of the formal machinery of talking about probabilities and propositions. Then in the next video, I will talk about some of these basic concepts or rules for calculating probabilities in a formal way. And then we will revisit the coin example from the very beginning and use our formal precise rules to shed some light on the questions that arise from the coin example. And in doing these things, what we will learn how to do are as follows. First, we will learn how to represent probabilities mathematically. Second, we will learn how to calculate some basic probabilities using some basic rules. And furthermore, some of these basic rules rely on the notions of independence and mutual exclusivity, which we talked about last week. So we will also talk more about how to tell the difference between independence and mutual exclusivity, because being able to identify one and the other are essential to being able to apply some of these rules to calculate basic probabilities. And finally, most of what we introduced today we will return to in more detail over the next few weeks. So today is really giving you the foundations of calculating probabilities in a formal and systematic way. So we begin with an example with a coin to illustrate some of the intuitive things, or to illustrate in an intuitive way some of the calculations that we will be using our formal rules to do. So I want you to suppose that I'm going to toss a fair coin twice. Now here are three possible results. First is that both tosses might land heads. Another possible result is that both tosses land tails. And the final possible result is that one toss lands heads and the other lands tails. But note here, I'm not talking about any particular order in which the heads and the tails come. So it could be that. So all that this is saying is that one of the two tosses is heads and one of the two tosses is tails. So that is the third possible outcome. That is, to summarize, we could have both heads, both tails, or one heads and one tails. Now we might ask, how probable is each of these three outcomes? So given that these are the three ways things might go, you might get two heads, two tails, or one of each. Reflect briefly on how probable you think each of these outcomes is. A natural answer that suggests itself is that because these are the three possible outcomes, each of them has a probability of 1/3. However, that is the incorrect answer. With a fair coin being tossed completely randomly twice in a row, each of these outcomes it's incorrect to say that each of these outcomes is equally probable, i.e. if these three are equally probable, that is to say that each of them has a probability of 1/3, that the total probability of one is split equally between these three possibilities. But that might be an intuitive first answer. However, that is wrong, and we will see now intuitively why that is wrong, and then we will build up some of our basic tools of probability theory, and then at the very end of this lecture, we will see more in a more deep way why that is the wrong answer. So the right answer can be seen as follows. There are actually 4 possible outcomes that are relevant here. And it's true that among those 4 possible outcomes, they're all equally probable. So here are the 4 most fine-grained outcomes of tossing a coin twice. We have the case in which you get heads on the first toss and heads on the second toss. That's at the very top. On the bottom, we have the case in which you get tails on the first toss and tails on the second toss. So those 2 outcomes, the first and the second, those correspond to the first 2 outcomes here, that you get 2 heads and 2 tails. But the third outcome, where you get 1 heads and 1 tails, that actually corresponds to 2 of these more particular or specific outcomes. So in the second outcome, we have heads on the first toss and tails on the second. But there's also the possibility of getting tails on the first toss and heads on the second. So between these 4 possibilities, or these 4 outcomes, each of these gets 1/4 probability. So that means that the probabilities of our initial 3 outcomes are as follows. 2 heads is just the exact same as this first outcome, so the probability of getting 2 heads is 1/4, as it says. Getting 2 tails is the exact same as this last outcome, where you get tails on the first and tails on the second, and that is 1/4. But what's crucial to notice is that when you talk about the possibility of getting 1 of each, i.e. 1 heads and 1 tails, that encompasses both of these more specific outcomes. So it encompasses the case where you get heads first and tails second, but also the case in which you get tails first and heads second. So that means that the probability of getting 1 of each, you have to combine these 2 probabilities of these 2 more particular ways of getting 1 of each. And because they're both 1/4, the probability of getting 1 of each is actually 1/2. So you do not split the probability equally between these 3 outcomes, as might be intuitive. Rather, you have to understand that when we're thinking about flipping a fair coin twice, the probability is split equally between these 4 outcomes, all the most particular ways of there being a certain sequence of heads and tails. And then when we consider some less specific thing, like for instance getting 1 of each, we have to group together the relevant more particular ways. And in this case, we group together the middle 2 outcomes and we get 1/2 probability for 1 of each. And that is the correct answer to our question about flipping this coin. So now in the rest of this lecture, what I'm going to do is I'm going to present to you some of the basic formal ideas, and then we'll return to this example and work through this using those formal ideas. And that is to say, there are a lot of complex probability concepts even in this example that we just worked through. So we're going to introduce I'm going to introduce you to them right now. So I begin by talking about probabilities and propositions. And this is effectively connecting our formal study of probability to the formal language that we developed in the previous unit. So this will become clear in what follows. So I want you to recall that when we were talking about sentences of our formal language, we were talking about propositions or statements that correspond to declarative sentences of natural language that are either true or false. So here are some examples of basic propositions or basic sentences. The first toss will land heads. This is a basic statement which is either true or false. Okay, and so this is a kind of basic atomic sentence that we would talk about in our language of our deductive logic. And similarly, we don't have to be talking about things like tossing coins. We can talk about anything. So another basic sentence is, for instance, that you will pass this class. Or we can talk about more scientific examples. So here's another basic sentence for us. For instance, the average temperature of the planet will increase at least 2 degrees by 2050. So these are all the kinds of basic claims of natural language that are either true or false. And these are exactly the kind of basic claims that we use capital letters in our formal language from the last unit to represent. So we talked a lot about basic or atomic sentences or simple sentences in our formal logic, and those are just sentence letters. And those simple sentence letters translate basic declarative sentences. And we saw many examples of that when we were translating in the previous unit, and we will be building on that in this current unit. So it's important that we can make claims with these basic sentences, and when we formalize them to talk about their probabilities, we use the same formalization using capital letters. And we will see also that we will use the same connectives to build up more complex sentences from basic sentence letters, and then talk about or ask about the probability of those complex formulas. So that is to say that we can ask about the probability of a proposition. And formally, when we talk about the probability of a proposition, we write this by writing a PR, which is short for probability, with some brackets, and in the dots that fill in, that go inside these brackets, we write the proposition or the sentence. So let's suppose that we are investigating a murder, and there's two relevant propositions that we are wondering about. The first is that Alice killed the butler. We're wondering whether it's true whether Alice killed the butler, and we're also wondering whether instead maybe Banu killed the butler. So when we start trying to formalize the way we talk about these propositions, we can use, for instance, the simple sentence letter A to stand for or translate the simple proposition that Alice killed the butler, and we can say that B will stand for the simple proposition that Banu killed the butler. And then when we ask what the probability is, say, of whether Alice did it, what we do is we write formally to PR to stand for probability of A. So the probability, or the PR of A, equals 1/3. And that means that the probability that Alice killed the butler is 1/3. Now we can assign any number here, but as we'll see shortly, this number has to be between 0 and 1 inclusively. So it could be 0, it could be 1, or anything in between. Okay. So when we're wondering about the probability of some claim, we're wondering what number between 0 and 1 it is. So if we think that there is a 1/3 probability that Alice is the murderer, we would write that formally by writing PR of A equals 1/3. So a little bit more formally, this PR thing stands for a function, and the function takes in as this argument a sentence and outputs a number. So the probability function gives you a number, which is a probability of the sentence, which is this argument. So when we write PR of A equals 1/3, we're saying that the probability that Alice killed the butler is 1/3. Now, instead of writing out particular numbers, we can also make claims as follows. We can say that the probability of A equals the probability of B. And what that means is that Alice and Banu are the murderers is equally likely. Or to put it another way, Alice and Banu are equally likely suspects. The probability that Alice did it and the probability that Banu did it are equal. And just as in our deductive logic from the last unit, we saw how we can form complex propositions with the logical connectives. We can also ask about the probability of complex propositions. So I'm going to just talk about the following formal equations. So this one here, PR of not A equals 3/4. Now considering again our translation where A equals Alice killed the butler and B equals Banu killed the butler, just take a moment to reflect on how you would read this out to yourself in ordinary English. So the answer is that the way to understand this is that the probability that Alice did not do it equals 3/4. That is to say, another way of putting this is that the probability that it's not true that Alice killed the butler equals 3/4. So we can negate an atomic sentence and ask about the probability of the negation. And that will be some number between 0 and 1. So we just kind of interpret these complex sentences in exactly the same way as we do in deductive logic. And then we stick them into the probability operator, and they are assigned a number. Now, how would you read to yourself this? So the way to interpret this formula is that we are saying that the probability that either Alice killed the butler or Banu killed the butler equals 1/2. So the probability that either Alice did it or Banu did it is 1/2 or 50%. So again, here we have a disjunction, the V, between two atomic sentences, and we've stuck that into the probability operator and wondered about the probability of the disjunction. So I think there's a couple more here. So just as above, where we could say that the probability of A equals the probability of B, we can also say that the probability of not A equals the probability of A and B. That is to say that the probability that Alice did it, that is to say that the probability that Alice didn't do it equals the probability that Alice did it and Banu did it. So maybe they work together in that case. So when we can join A and B and ask about the probability, we're kind of asking but the probability that Alice and Banu did it, which is to say that maybe they work together to commit this murder. Okay, so to conclude this first video of this lecture, I'm going to very briefly make a comment about other applications of probability theory, which we are not going to go into any more detail, but I will flag, which is that one major, perhaps the main application of probability theory is in statistics. And you might have seen this in high school, or you might see this in your university career. But in statistics, they talk about the probabilities of events or sets of events, and as opposed to the probabilities of propositions. Now, I just want to note that whichever you choose is basically the same. They're just two different ways of talking about the same thing, and this is covered in a bit more detail in the textbook. But I just wanted to flag that if you have done statistics or will do it or are doing it currently, there is a lot of overlap between what I'm saying here and what you do in statistics, despite the fact that there might be some superficial differences in talking about events versus propositions. But that is just a brief note, and we're not going to explore that statistics in any detail in this class.